Okay. Any questions about anything? Questions? Questions? Okay, so anyway, let's pick up where we left off last time. We were talking about specifically spectrograms, but more generally the whole idea of time, frequency analysis, of signals, and essentially what this does is enables you not only to talk about what's going on in a signal from a spectral / frequency domain standpoint, but when that various content is going on. So what you're getting a grip on here, not only quote unquote spectral happenings in a signal, but quote unquote when the happenings occur. And the tool, like I said, we're going to use for this, or I shouldn't say the tool, the time frequency domain analysis thing that we're going to develop is the spectrogram, and the spectrogram is based on a math tool called the short-term DFT. And that was what we introduced at the end of class last time. I want to remind you, so the main tool we're going to use is the short-term DFT. I won't write out the words again this time, or short-time DFT, whatever. And it involves some user choices. So the user choices here, remember what they were? You had a sequence of what we call analysis times. So an increasing sequence of analysis times, as they're called. And usually this looks like this. 0, cap R, cap 2R, and so on for some fixed R bigger than 0. And the notation we use for a generic analysis time is going to be n sub s. That's what the book uses. So we use n sub s to represent a generic analysis time. Okay, so that's the first user choice. Second user choice is a window length, an analysis window length, capital L, and we're going to have to choose this for reasons that will become clear in a minute. So for reasons to be explained, we need that cap L is bigger than cap R. Cap R is the distance between consecutive analysis times. Cap L is the length of the analysis windows. Along with an L point windowing function, W of N. And so this guy could be rectangular window, could be a Hamming window, could be a Hahn window, whatever you want to call it. It could be any one of those windowing functions. Okay. And finally, some N. And this cap N is going to be bigger than or equal to L. All right, so given those user choices, what is the short term or short time DFT? So for each analysis time n sub s and each k, where k runs from 0 through n minus 1 inclusive, you define x hat bracket k comma n s by means of the following equation. X hat of k comma n s equals sum from little n equals 0 to n minus 1 of w of n times x of n. And by the way, x of n is the sequence, the signal you're analyzing using the short time DFT. I forgot to write, or I didn't forget. I was going to remind you of the context here. You have this long discrete time signal x of n. Sometimes it comes from sampling, even this time signal, but whatever. X of n is the thing you're analyzing. W of n is the windowing function times e to the minus j n k, actually, sorry, x of ns plus n, e to the minus j n k, 2 pi over cap n. And that's for 0 less than equal k less than capital. Okay, so that's what x hat of k n s is. Now what's the basic idea? The idea is that you look at the signal from time ns through time ns plus L minus 1. So if you take W of n times x of ns plus n, n running from 0 through L minus 1, that is an L point signal and what values does it contain? It contains the values of x of m for the time range n sub s less than or equal to m less than n sub s plus L. So it's a window of the signal x of n, the one you're trying to analyze. This is the n point DFT of that L point signal. We're always allowed to take an n point DFT of an L point signal when n is bigger than or equal to L. So x hat of k comma ns, 0 less than or equal to k less than n, is the n point DFT of this L point signal. Okay, so that's a description of the short time DFT. Right? So any questions about that? I know it's a lot of notation to swallow at once, but you know, we've done that before. Okay, and I summarized that. Remember what last time I said, procedurally what you're doing is this. You're going to each analysis time, you're looking at L, ahead of that you're looking at that window, and then you're taking the short time DFT, or you're taking the endpoint DFT of that where n is some bigger than L thing. Okay, so what do we do with this? What do we do with the short time DFT? We build what's called a spectrogram. Okay, so what is a spectrogram? So having computed all these, the x hat of k comma ns, we build what's called a spectrogram as follows. And there's lots of ways of doing this, and the way I'm going to describe is just one way of many described here. All right, so what do? We make a plot. What is the plot? The plot is going to have m on the horizontal axis and k on the vertical axis. So you make a plot. M is on horizontal axis, and k is on vertical axis. Okay. What do you put at the m comma k position in this plot? You put a blob, and the blob is just going to be a grayscale thing. So it's going to be darker if the number associated with it is higher. It's going to be lighter if the number associated with it is lower. So it's a grayscale plot. And we've already discussed the controversy about whether you spell gray with an A or an E. I like to spell it with an E, whatever. It's a grayscale plot. And what is the darkness of the point at M comma K? So the point at M comma K in this plot has darkness on the grayscale proportional to what? Well, what we do is we look at that time M. M is going to be a time thing. And we look at all the different analysis windows in which M falls. Okay? And we look at all the values of the short time DFT over those analysis windows. So it's proportional to this. The sum of the magnitudes, we're only going to deal with magnitudes here. That's the cool thing about spectrograms. You don't even worry about phase, just think about magnitudes. Of all the x hat of k, comma, and s's. And what is this sum? The sum is over all the ns values for which M falls in the window, the analysis window, n sub s less than or equal to n less than n sub s plus L. Okay? Again, it's a mouthful. It's a bunch of notation. Let me draw a picture. Okay, let me draw a picture. Is that all right? You object? Okay, good. No, you don't object. Okay. Here's a picture. So you think of M as running on this axis. And it starts at 0, right? And here you have, say, R. Here's 2R. Here's 3R. Here's 4R. Here's 5R. So on, 6R. Those are your analysis times. And suppose you pick L to be like 1.3R. So here are going to be your analysis windows. One of them is going to go out to here. One of them is going to be from here to here. So let me draw lines in there. Another one's going to be from here to here. Another one's going to be from here to here. And, so just drawing them this way so that you can kind of see where they are. So the lengths of all these guys are going to be L. Those are going to be your analysis windows. So these are all the analysis windows. All right? Now let's pick an M value, a little m value. Say our little m value is just over 5R. So let's call that M. The labeled M, the M labeled in the picture, the labeled M value, which is just bigger than or equal to 5R, lies in two different analysis windows. And which ones are those? Those are going to be the analysis window that starts at 4R, so 4R less than or equal to n less than or equal to, or less than 4R plus L, and 5R less than or equal to n less than 5R plus L. let's put n in there. That's just to keep it, to match it up over there. So it lies in both of these analysis windows. Thus, that sum is going to be the grayscale dot at point m comma k has darkness, shade, whatever, proportional to this sum, magnitude of x hat of k comma 4r. That's one of the ns values in whose beginning at ns analysis window m falls, plus this x hat of k comma 5r. All right, so that's just an example, a picture. All right, so now what I want to do is first of all, I want to tell you the intuition behind what the darkness of the grayscale spot at m comma k has to do with frequency, behind the link between those two, or frequency content or whatever. And then I want to look at the user choices and their influences and how they trade off against each other. And I always want to tie this back to music, okay? Because this is a really good way to understand why spectrograms are important. All right, so what's the intuition behind the spectrogram? Okay, the intuition behind the spectrogram is as follows. That if you have a dark spot at MK, so a dark spot at the MK point in the spectrogram, and now you can sort of see now, remember I told you last time that I didn't like the fact that the book puts K before NS, because the spectrogram always has time on the horizontal, always has frequency on the vertical, so I would prefer it to be NS comma K, but it isn't. Okay, a dark spot at M comma K means roughly that quote-unquote X of N has significant frequency content, significant, and of course we're talking discrete time normalized frequency content, significant frequency content near frequency k 2 pi over n at around time m. Okay? So you look at the spectrogram, you see what's dark. You see something dark at, say, time m equals, 10,000 and k equals 7, then you know that around time 10,000, X hat has frequency content, significant frequency content of this frequency, around that frequency. Okay, so that's the intuition, roughly speaking, the intuition behind the spectrogram. Okay. Now, what I want to do is I want to look at this. So the plot does tell you not only what's going on spectrally, but kind of when it happens. But the thing is, there's a lot of user choices here, and like I said, they trade off against each other. Let's have a look at those. Okay, so what we want to do is we're going to look at all the user choices and see what influence they have. So see how they influence the spectrogram and trade off against each other. All right? All right, so first off, and again, let's think music. So think music. And I want to think specifically about two cases. So two sort of things you'll encounter in music a lot. On the one hand, you have melodies. So two situations. One situation is melodies. What are melodies? They are just sequences of individual notes, one after another. So these are time sequences of individual notes. And the other situation is chords. Okay? Chords are length of time where different notes are played simultaneously. So several notes played simultaneously for a bit. And I'm not using the word bit in the Tukey sense, the technical sense, obviously. Using it in the colloquial sense. Okay. So first of all, remember I told you when I was talking about the user choices that we had to pick L bigger than R, where R is the difference between consecutive analysis times. So first off, why do we need L bigger than R? L is the length of an analysis window, R is the distance between analysis times. We need this so that every M value falls in at least one analysis window. Right? Because otherwise, if L is less than R, then there's going to be some M's that get missed because the first analysis window will start here, the next one will start here and end here, and all these guys toward the end of the interval between analysis times will get missed. Jack? Yeah, I mean, theoretically you could let L equal R, but no one ever does. Everyone always lets it be like, 1.5R or 2R or something like that. Okay. All right, so that's one thing we want to get out of the way. Second thing, okay, what is the choice, what is the effect of the choice of R, the distance between analysis times? So what about the choice of R? The distance between analysis times. Consecutive analysis times. Why might we want R to be big, small, whatever? Obviously, what is the smallest R could possibly be? This is obvious. Anima. Yes, 1. R could be 1. Every single time could be an analysis time, but that leads to an incredibly complicated situation computationally. You don't want to go there, all right? So theoretically, we could set R equal to 1, but that's computationally wasteful. And gives rise to other problems that I don't even fully understand. So we want to let R be something bigger than 1, whatever that is. What if we make it too long? What if we make it too short? What does that mean? Well, so imagine you had a picture like this up here. Let's blow it up. So let's zoom in on this situation. You have time 0, you have time R, you have time 2R in the signal. So, and here's your analysis window. Say it goes out to here. Remember, they always have to be longer than the distance between the consecutive analysis times. All right, now suppose that in this patch here, so suppose that in here you have a rapid run of notes, a melody that takes place right in between these times. So say you have a quick melody in here. All right, so think fast. Think of, Flight of the Bumblebee, right? You ever heard of that? I think it's by Rimsky-Korsakov. I have to look it up, though. Anybody know if it's by Rimsky-Korsakov? Alexander, do you know that? No. Yes. Well, I think it is. Anyway, Flight of the Bumblebee has all these really fast runs of notes, right? And if you have a fast run of notes in here, okay, it's only captured by one analysis window, okay? And so what happens is that, and say that the previous one ended before, okay? It's only captured by this one analysis window, and when you look at a run of notes in an analysis window, that doesn't tell you that it's a run of notes. It just says that, quote unquote, in this zone, the signal had frequency content at, say, these 4 notes. It doesn't tell you that they were consecutive to each other. It just tells you that there's an A, a B flat, a B, and a C in this interval somewhere. Okay? So the problem is here that because the first and second analysis times are close, because all these guys fall in only one analysis window and so on, you can't tell from the spectrogram, in fact from the STBFT, that this is actually a melody. And not just a chord with those notes in it. All right? So it might as well be a chord or some other sequencing of the notes other than the actual sequencing. All right? So what people say, the spectrogram scholars of the world, of which I'm not one, say that you want to choose. So here's the mantra, okay? You want the analysis times to be close enough together to track the rapidest variations in the spectral content of the signal you're analyzing. So here's the sort of the wisdom that goes along with this, quote unquote. You want R small enough, that is to say, the analysis times close enough together to track the rapid, let's put it this way, track the most rapid frequency content variations. And when I say rapid, I'm referring to time here. So frequency content variations in the signal you're analyzing. And clearly that's going to depend on the signal, right? So you might use a bigger R if you're dealing with a signal that has these long, drawn-out, slowly played notes and whatever. That saves you computation, right? So clearly this is signal dependent. And one of the recurring themes here is that when you're actually doing a spectrogram, what you often have to do is tweak. You play around, you try one R, you try one L, you try another, until you get one that looks good. Okay? So, I forgot the end quote. All right. So that's one user choice. What about the choice of R? You want to make it small enough to track the rapidest frequency content variations in the signal you're analyzing. Okay, what about L? What about L? All right, let's do N first, because L is the most involved and interesting, in a sense, one. Okay, so what about N? What about N? N is the length of the DFT that you're taking of the L point window of the signal. So you take all these L point windows of the signal, and for each of those you take its N point DFT. What does the N point DFT do? It just gives you a more refined sampling of the DTFT of the L point signal, W of n times x of n plus s. X of n and s plus n. So larger n implies a more refined, quote-unquote, sampling of the DTFTs of the L point signals, W of n, x of ns plus L, or ns plus n. These are the, let me write this. This board is so annoying, you know, there's that and there's this, and they both bother me so much. So, W of n, x of ns plus n. Okay, so for each ns, there's one of these L point signals. You're going to take the N point DFT of that. The fact that N is bigger than or equal to L, that makes it possible to do that. The bigger N is, the closer together the samples of the DTFT of the signal are that give the N point DFT of it. Okay. And what it does, the end result is, in the spectrogram, is just going to be a finer scale on the quote-unquote y-axis, the k-axis in the spectrogram. So vertical axis, let's call it vertical. The distance between consecutive k's is going to correspond to frequency difference of 2 pi over n instead of something less. So the distance between adjacent k's is going to be 2 pi over n, which is obviously smaller when n is larger. Let's not use distance here. Let's say the frequency difference between consecutive k's on the vertical axis is 2 pi over n, which is smaller when n is bigger. And you might say, okay, well, we always want the most refined plot we can get, so why not just pick n to be 10 to the 59th every time? You know, we get a nice refined plot. Why might we not want to do that? Why, Nick? Yeah, I took a CS major, right? But here it is. You don't want to do that. You don't want to take n arbitrarily large because bigger n means, again, just like when you take little n, the r small, more computation. So you have to trade off, again, computational complexity versus what you're trying to do. Okay? Good? All right, so that's the only effect of n. Now what about L? Like I said, this is the coolest one. So what about L? What about L, the analysis window? Length. All right, so I want to consider separately the melody situation and the chord situation and see what kind of effect we have here, what we have effect on those. So what we're going to do is we're going to contrast the melody and chord situations. All right? What about a melody? What about when you have a sequence of notes? What is the spectrogram kind of going to look like? So let's look at spectrogram, and there's pictures in the book. of this. And I thought about actually bringing the book with me today and saying, okay, everybody, pause the video, open the book to this page, look at this picture. But I didn't want you staring at the book instead of staring at what I'm writing on the board. So I don't know, that's kind of arrogant, but whatever. Spectrogram from a melody is going to look something like this. If it were perfect, so if perfect, it would, so here's your M axis and here's your K axis, and say the melody takes place out here, so you're going to have something like this. And suppose, these are 3 different frequencies. Suppose they're the frequencies for how about like, how about a major triad. So you're going to have A, C sharp, E. Okay? And that means that an A is held here, A happens here, followed by C sharp, followed by an E. Okay? Now, if it were perfect, there would be just no doubt at all of exactly where this A ended and the C sharp began, exactly where the C sharp ended and the E began, and so on. But in real life, it doesn't look that way. How come? So in real life, there's going to be like a blurry transition zone in between the notes. There's going to be a little interval of times. Okay, so in real life, you're going to have something like this. So you're going to have your A, C sharp, E, and you're going to have the A goes on like this, and then there's like this doubtful area where it looks like there's a C sharp and an A going on at the same time, and then this kind of doubtful area where it looks like there's a C sharp and an E going on at the same time. All right? So this overlaps with this, overlaps with this. So you have here, these are what I would call blurry areas that feature both A and C sharp or C sharp E. Even though the person playing the piano has awesome technique and the notes are really distinct, boom, 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 no overlap at all. I mean, you can do legato, well, I don't want to go there. Okay, so anyway, blurry areas. The person never is playing an A and a C sharp or a C sharp and an E at the same time, but the spectrogram seems to show that. Why is this? This results from having L be too long. So this artifact, if you will, this feature or bug, results from, quote unquote, L too long, so to speak. If you make L shorter, in other words, you can't tell exactly where the C sharp ends and where the E starts, where the A ends and where the C sharp starts. Where A ends, let's say when. When A ends and C sharp starts. There's this sort of region of doubt. Now, why does this correspond to L being too long? Why is it? Well, it turns out that like the only way you're going to get perfect is this. If your analysis times are exactly when the notes start, okay, and your L is exactly the length of time between analysis times. In other words, L equals R. That's the only time you're going to get this. You're always going to see a piece of the next note in parallel with a piece of the current note in parallel with a piece of the next note because of this overlap between consecutive analysis windows. And the bigger L is, the longer you'll see that overlap. Okay, so the idea here is, roughly speaking, it is the following, that each note, let's put it this way, the longer the overlap between consecutive analysis windows, the wider the mushy region, the blurry region in the spectrogram. Because, for example, C# is featured in 2 analysis windows and featured along with an A for a longer time. C# and A both. Feature for a longer time in 2 different analysis windows. Okay, so the long and the short of it is the following. Bigger L, worse time resolution. Okay, you can take that one to the bank. So I'm going to put this in a big circle. Bigger L corresponds with worse time resolution in the spectrogram. More fuzziness separating notes of melodies. More doubt about where one note in a melody ends and the next one begins. Okay. So you may say, okay, well, why not make L as small as possible? Why not shoot for that? You know, L equals exactly R, and just coincidentally pick your R, and so all the notes have the same length, whatever, you know. No, that's not how real signals are. And besides, it turns out that picking L too small gives you problems of another kind. Okay? All right. So what are those? And we want to talk about how these things trade off against each other. So what about quote-unquote L too small? What kind of a problem can arise when you make L too small? Well, now instead of thinking about a melody, we're going to think about a chord. So instead of a melody, think about a chord. Instead of a melody, and maybe let's think of a chord that, you know, it's some kind of 20th century Stravinsky-ish composition where there's lots of dissonance and there's notes that are really close together. So you might have like, you know, C, C sharp, D, E. That's a really dissonant chord, okay? So think about a chord instead of a melody, especially ones, especially chord featuring 2 close together notes. Okay, so let's imagine what a spectrogram might look like for that. So say the chord is happening here in this zone. What you're going to have is you're going to have like spectral stuff for one note. So say this is a C, and then the C sharp is going to be really close to that, so you're going to have spectral stuff here. And then how about an E? Let's make it far enough away so it's not really getting in the way. Okay, so in the spectrogram, this is what's going to look like. Now, I'm drawing these fuzzy because in a perfect world, these would just be perfect straight lines with no fuzziness around them at all. So in a perfect world, would be lines not fuzzy. Why are they fuzzy? Why are they fuzzy? Well, they're fuzzy because the DFT doesn't give perfect frequency resolution. What do I mean by that? In fact, the DTFT doesn't give perfect frequency resolution. So they're fuzzy because the DTFT and its sampling, which gives rise to the DFT, don't tell us exactly what the frequencies of the notes are because the notes have finite duration. They're not pure periodic signals. So they don't have perfect frequency resolution. Let me remind you what's going on with that. All right, so here, let me just schematically draw this. Say this is out to 2 pi, 0. And let's just say that this is the frequency corresponding to the C. This is the frequency corresponding to the C sharp. And this is the frequency corresponding to the E. Okay? Now the DTFT of a plain old C is going to look like this. It's going to look Dirichlet-ish, right? And the one here is going to look Dirichlet-ish, right? And the one here is going to look Dirichlet-ish. They're not going to be perfectly just aligned there. Okay, so these are like, this is a DTFT of a finite duration of a length L. Let's be really specific. C. This is the DTFT of a length L E. And this is a DTFT of a length L C sharp. All right? So you see there's some collision there. That's why the C is going to have a little bit of band around the exact frequency of the C and the C sharp around the C and so on. Now what does L have to do with this? Remember what L was? L was not only the height of this, but also L had to do with how far the first zero crossing was, how wide the central lobe is. Look, so let's zoom in on the C sharp thing. So let's zoom in on the C sharp. So here, this is the frequency corresponding to a C. This is the frequency corresponding to a C sharp. And you're going to have this going on. And then you're going to have that, blah, something like that. And then you're going to have this going on. Okay. So what is the first zero crossing going to be? It's going to be 2 pi over L to the right of the frequency. So this is C sharp plus 2 pi over L. This one here is C sharp minus 2 pi over L. This one is C plus 2 pi over L. So see what's going on here? The smaller L is, the wider the central lobe in the DTFT is, the farther the zero crossing is from the actual note, and the more collision you get between these two pictures. So, smaller L means wider central lobes, means more collision, quote unquote, between the spectra of the finite duration C and the C sharp. All right? So what happens when you lower L? Remember, lowering L is going to make the time resolution better. When you lower L, it makes the what? What kind? Okay. I heard someone say it. Heard someone say it. Who said that? Come on. You were right. No one wants to take credit. Smaller L messes up the frequency resolution of the spectrogram. And so what will happen is you'll get the C sharp and the C, there's going to be this blobby mass, and you can't tell. You know that there was probably 2 notes going on in there, but you don't know exactly what they were. So thus, smaller L corresponds with worse frequency resolution in the spectrogram. Okay, so those are the 2 things you can take to the bank. That bigger L, worse time resolution, smaller L, worse frequency resolution. So that's the kind of things, those are the kind of things that are trading off against each other. And if you have like a piece of music that's all chords, like a church hymn or something, versus a piece of music that's like all melody, like Flight of the Bumblebee, you might want to do things differently for those 2 signals. So every signal X of N is going to give you a different set of ST-DFT parameters that work to give you a good spectrogram. So generally in practice, these are the things you have to remember. So remember that different X of N's, different signals X of N are going to require different spectrogram parameters, or ST-DFT parameters, to get a nice plot, a nice spectrogram plot. Okay? And given a signal, you might need to tweak. You might need to try a different R, try a different L, increase R, decrease R, increase L, decrease L, whatever. So in general, what you're going to end up doing is, given X of N, you often need to sort of repeat the process, sort of tweak the parameters, and redo until you get what you want. You get a good enough result. Good enough plot. Okay. Great. So this is good. I mean, I'm happy that this year I got to spend a little more time on the spectrogram thing than I did last year. There's one last thing I want to say about these spectrograms, and that is all about, rescaling the axes to get back to like continuous time frequencies and whatever. And this, I'll just be real quick about this. So a brief word about axis rescaling, etc. Okay, first off, remember that the background picture we started with was we had a continuous time signal x of t that we sampled as fast as you want. Okay? So recall that the background is you get the signal x of n that you're analyzing from sampling a continuous time signal x of t. And assume you do this fast enough so that you can, I mean, x of t is going to be time, have finite duration, therefore it's not going to be band limited, but you can think of x of t, if it's a piece of music, say, as having its frequency content all between plus and minus 20 kilohertz. So sample it at 44,100 hertz, whatever, you should be fine, whatever. So fast. So let's assume that whatever frequency content in x of t that's outside of the Nyquist zone is negligible. So x of t has negligible frequency content outside of, say, f max, and assume that fs is bigger than 2f max, where fs is the sampling frequency. All right, so that's how you get your signal x of n that you put through this spectrogram generator. Okay? Now you have your x of n, you make your user choices. You choose your n sub s's, you choose your L, you choose your cap n to do the endpoint DFT. And so when you do the spectrogram for x of n, okay, and of course we assume that x is a real continuous time signal, as usual, so it's real numbers. When you do the spectrogram for x of n, it suffices to have the vertical axis, the k axis, so to speak, encompass only the frequencies out to pi. So it suffices to limit the quote-unquote, well, the vertical axis, the one on which we plot k, to, say, 0 less than or equal to k less than n over 2. How come? Because this corresponds to k equals n over 2 corresponds to omega hat equals pi, because k equals n corresponds to 2 pi. And all of the frequency content in x of n is going to be within 0 to pi because of the speed of the sampling. So speed of the sampling puts all the frequency content of x of n inside pi. And the frequency content that's out near 2 pi by realness of x is conjugate symmetric with that. So it will be conjugate symmetric, so to speak, conjugate symmetrically copied, quote unquote, out near 2 pi. Like whatever goes on from 0 to pi on the vertical axis goes on conjugately from 2 pi down to pi on the vertical axis. So we don't have to worry about that because it's just a copy. All right? So thus your axes are going to look like this. You're going to have m here. That's the number of samples. And up here you're going to have k, and we're going to have k equals n over 2. Now what you might want to do is rescale the up and down axis so it's omega hat. And that would be fine too. That's one thing, one step in the rescaling process. So you can then rescale the vertical axis to be labeled by omega hat. So what does that mean? That means that the k equals n over 2 is going to correspond to pi, and any other k in between there is going to correspond to k to pi over n. That's equal to omega hat. So all that means is you're relabeling, like that one you're relabeling pi, k equals n over 4, say if n is a multiple of 4, you're relabeling as pi over 2, and so on. And sometimes, because of the way like music is, where you have an octave, it's double the frequency, you know, that you have this sort of logarithmic thing going on, or exponential thing going on, sometimes people have log k, or log of omega hat as their vertical axis. So often do log of k, or log of omega hat for vertical axis. And just make sure you label it right. And finally, you can refer it back to continuous time. So you can rescale to get a view of the spectrogram of the original continuous time signal x and t, by rescaling the m axis to what? T equals mts. So rescaling both axes as follows. The m on the m axis is going to go with mts, which is m over fs, whatever. This is t equals that. And the vertical axis, omega hat, is going to go with what? I just have to do this in my head individually each time. Omega hat equals 2 pi fs, right? I want fs over 2 to go to pi. So omega hat is 2 pi fs. So f equals, here. No, 2 pi fts. So f is equal to omega hat over 2 pi ts. Yeah. All right. So that means omega hat equals pi corresponds to 1 over 2 ts, which is fs over 2. Excellent. All right, so that's the story on spectrograms. Any questions about that? Okay. All right, so what's the next thing we want to talk about? And this is kind of the last family of topics for the whole semester we're entering. You know, we're coming into the home stretch here. And if you look at the book, it'll look like we're skipping a chapter, but we're not. Okay. The book, in the chapter after this one, the one we just talked about, the book does a lot of trivial stuff about Z transforms for FIR systems and finite duration signals, and I just think it's, you know, it's better just to go for the jugular and do, you know, jump right into IIR systems, define the Z transform in that context, and then look back at the FIR stuff as a special case. You may disagree, you could read that chapter, fine, you know, whatever, but I think it's kind of a waste of lecture time to cover it, because it's all just a bunch of polynomial algebra. What we really want to do is we want to think about the signals and systems aspect of FIR systems. So that's what we're going to, or of IIR systems. So that's what we're going to spend the bulk of the rest of our time on. So the final sort of topic family that we're going to be dealing with is going to be IIR systems, Z transforms as a tool for analyzing these things, etc. And along the way, we're going to encounter some important concepts. Things like transfer function. How many people have heard of a transfer function? Yeah, if you took circuits, you've heard of transfer function. How many people have heard of poles and zeros? Yeah. Well, they're a little different in discrete time, but we'll see there's a lot of similarities. Stability, do you know about stability? Like, there's no problem with stability for FIR systems, but there turns out to be... Anyway, we'll get to that. All right, so IIR system. What does IIR mean? It means infinite duration impulse response, and we're going to see why the systems we look at have infinite duration impulse responses by hand calculating them. We're actually going to figure out some impulse responses with these systems. But we've already seen one IIR system before. Back, or it's more like over there, when we were in Phillips 219, I remember talking about this. I talked about the so-called Discrete-Time Integrator, and we figured out the impulse response of that was a unit step. That was our first IIR system, all right? But the ones we're going to focus on, and it turns out you can cast the integrator in this light, so we're going to focus on causal systems governed by difference equations of the form, and I'm going to write it the way the book does it, y of n equals two sums. Instead of just having a sum of bkx of n minus k, you're going to have the sum from k equals 1 to n of ak y of n minus k plus the sum from k equals 0 to m of bk x of n minus k. Okay, so check this out. You've got previous y values here in the first sum, linearly combined, and now you have previous x values like we did before. So without this part, it's our old friend in FIR system. With this part, it's not. All right. Now, there's no reason to assume that the cap m and cap n in this picture are different. You can just pick the bigger of the two and have all the remaining coefficients be 0. So you gain nothing by letting m and n be different. So what we're going to do is just let cap n be the bigger of the two, and that's a little deceptive. And I'll do it anyway. And set y of n is equal to the sum from k equals 1 to n of ak y of n minus k plus the sum from k equals 1 to n of bk x, k equals 0 to n of bk x of n minus k. All right? So that's the general form of the systems we're going to look at. Now, I claim that we need to be careful. We need to be more careful than the book is in understanding what makes this an I/O system that takes x's to y's. So we need to do some extra work to make sure that this equation here gives rise to a well-defined I/O relationship. So we need to be careful to ensure that this leads to a well-defined I/O relationship. So in other words, a box that takes signals x of n and gives you outputs y of n. So you need to have a situation where x of n determines y of n by means of the system. Now, why do you have to be careful? Well, when we had an FIR system, we had none of these terms. It was clear how to compute y of n from x of n. If you give me the signal x of n, I can figure out what y of n is for all n. But from this equation, it's not so clear because there's this recursive aspect to it. There's this piece of the past of y that plays a role in computing the future of y, along with the present and past of x. So that's the wrinkle we have to iron out to make a picture like this. And the way we're going to iron that out is restrict the universe, so to speak, and I'm going to use that word a lot in the next couple days. Restrict the universe of signals that we're dealing with to be signals that are 0 for n less than 0. So to do this, the step I take here is, to that end, what we're going to do is restrict, for now, I want to emphasize for now, because later on, when we talk about frequency response, we're going to have to go back to all signals. Restrict for now our attention to the universe, quote-unquote, universe of signals that are 0 for n less than 0. So they start at time 0 or after. So all the signals we're going to be considering for now are in this universe. For such signals, this difference equation defines a well-defined I/O mapping. Okay? If you give me a signal in that universe x of n, and I'm assuming y of n is in that universe, I can compute y of n uniquely from this difference equation. Now, the book has a name for this, what I'm doing here, restricting our attention to this universe of signals. They call it, quote unquote, look at the difference equation subject to initial rest conditions. So the caution, the book doesn't use the U word. Again, so we have a little difference with the book. The book talks about analyzing the difference equation, quote unquote, starting from initial rest conditions. Amounts to the same thing, but it's not quite the same. It's not quite the same because they're a little bit sloppy about how, in what sense, are signals like this actually linear and time invariant. Anyway, that's enough for today. We'll pick this up next time. And as always, I miss you guys. And I'll see you soon, I hope. And I hope you're doing okay. All right. And so now the multi-step lecture termination process, or process, as they would say in Canada. Here we go. Whoop. It's not working for me. All right. Click number 1. Click number 2, and I'll see you soon.